Bismillah ar-Rahman ar-Rahim. Welcome back, everybody. Continuing with IQ files. So I got recommended to use real environmental signals. So we can try this software tool called SDR++. It's really cool. Right now I'm on the FM broadcast band. We have a FM station here in Saudi Arabia at 100 megahertz. We can go to different frequencies. But just to stick with the topic of IQ recordings, what we can notice from this tool is if we just scroll down, there's a tab here called Recorder. So I'm going to go ahead and record baseband for IQ, not the audio. So I'm just going to hit this, let it run for about 5 seconds. Okay, stop. Okay, so it's going to make a file for me. This one here just got made, and it's about 42 megabytes, and I'm just going to use this file that I made right before this video. It's a similar amount of bytes, but anyhow, we can go to the script. So let's see how can we use these files, because it says a WAV file, but if I try to play this right now, hopefully it doesn't crash, but yeah, it's not going to be anything useful. So what we can do then is let's load it into Python. So it's really easy, just one function, numpy.fromFile, and then the name of the file. And unlike last time we used this SDR tool called RTL SDR, and it saves the IQ samples as 8 bits or 1 byte. Here, with this SDR++ software, it saves, in the user manual you can see it uses 16 bits. So that's double the amount of bytes, so the file size will be bigger, but let's just go along and see what to do with them. So the first thing to do is to change the data type here to int16. Last time we used uint8, but if we go ahead and just run this again, so I put the file size here, and we're loading this entire file into this array, and then I'm going to take the file size and I'm going to divide it by the length of the array, and it's going to tell me that we have 2 bytes for every element of the array. So it's double compared to last time. So let's look at some elements. I already ran this, so I print out the first 6 numbers of the array, so we can see it's not ranging from 0 to 256 like last time, obviously. I'm going to do the max and the min value, which is, it goes up to 30,000 and down to negative 32,000. And the reason that is because with 16-bit integers, signed ones goes from negative 32,768 to positive 32,767. So now, what we notice when we see these is, again, these are not IQ samples. These are int16s, so a type of data. So we have to do the same thing as last time with a small change. Now when we normalize, we're not going to divide by 256, and we don't have to multiply by 2 and minus 1 because the data is already signed. So the maximum 16-bit integer, or the maximum value, is 65,536, but what we do is, to make it signed, is we're going to take one of these bits and we're going to reserve it just to tell whether the number is positive or negative. So we're actually going to use 15 bits. So our maximum value is going to be 32,768. But this allows us to go from negative 32,000 to positive 32,000. So to normalize this data then, we're just going to divide every number there by 32,768, and we'll get something like this. So 0.572. If we see this first value, 18,770, let's do 18,770 divided by the maximum number, which was 32,768. 32,768. It's 0.5728. So that's this number here. And then the second step to do is to combine the numbers. So this is not IQ, these are all just plain numbers. So we're going to take the first number plus j times the second number. And that's what this line did here. So it's these same two numbers, but now they're joined together. Okay, so now we can, you don't have to do this, but as a sanity check, we can note the sampling rate that we were using, which that shows right here, 1.92 megahertz. And if we use that number here with the length of the array the IQ array, that's going to give us the number of seconds. So we know we made about a 5-second recording. So this lets us know that we're doing things correctly. So we can plot like last time, which I already plotted them. And we can see here's our IQ samples. We have something weird going on here. And to know what that is, let's take a look at the file. So here's our file. You can see the name of the file. It says baseband for IQ, 1 million hertz. So this is the frequency that we were on right here, 100 megahertz. And then it has a 13, 22, 35. This is actually a timestamp, and 6/12/2024, December 6, 2024. But you can see it's trying to save some extra data here that doesn't really have to do anything with the IQ samples. So let's investigate. Why do some of the samples look weird? And this is the reason. So right at the beginning here, you can see this. It says riff, wave format, and then a bunch of characters and then data. So this is obviously not the IQ samples themselves. This is just some data that got added by the software. So there's two things we can do. We can just delete it here. So if I go to the beginning and just hit delete, I can keep deleting that data, right? That's one way to do it. Or what I can do is I can just make note of where it started. So, or sorry, where it ends. So if I just go to where this part that I suspect is the metadata, you can see I'm just gonna cut it off at around 42 here. Let's go to 44. This is probably safer. So what I can do is I can reload this. Remember, every 2 bytes becomes 1 element, so instead of 44, I'm going to use 22 divided by 2. And then we can normalize it again, get it into the IQ format. And I'm going to do something called indexing. So I'm going to call this snapshot, and I'm going to take this array, and I'm going to take the first 1,000 elements, and I'm going to plot that. So now we got rid of that junk data that has nothing to do with the IQ samples, and we're left with just the IQ samples. Okay, and what we can do also, we can plot the power spectrum like last time. You see, if you think this looks weird, that's because this is actually, what we did is we running this function PSD, power spectrum density, on the entire array, all 5 seconds in one time. So it's not going to look like this. This is a live playback. So what we can do is we can do more indexing. So I can say index equals 0, and I can say index to index plus 10,000, for example. So this is the power spectrum of the whole 5 seconds averaged together. So it's very smooth. But if I'm going to take just the first 10,000 samples, now it looks more like what we expected here. And now with indexing, what we can do is say I don't want to go from 0 to 10,000. Let's go from 10,000 to 20,000. So this is going to give me like the next snapshot, slightly changed. And you can keep doing this till the end of the file. Or there's a better way. Instead of looping through it in Python, what we can do is we can save this array, this IQ samples that we just made. So we're going to just take the name of the array, .as type, complex64. I can explain this more later, but it's a data type that GNU Radio software uses by default. And you say .to file, and then you make any file name that we want. I'm just going to call it strpp_new.iq, and then we're going to save this. Okay, now we save this IQ recording, we can go to GNU Radio. So GNU Radio is much better for live playback. Unlike Python, Python is if you need to take your time and look at one snapshot at a time. But for GNU Radio, what we start with is just a file source if we want to use IQ recordings. And I already did this here, so I put the path to the file, and I'm just going to add this throttle block. So it says the documentation says to add this if we're not using any SDR hardwares, just if we're using file recordings. And I'm going to add a time sync, a frequency sync, and a waterfall sync. I'm going to go ahead and press repeat. I made the repeat option no, and I'm going to just press play here. Okay, so here's our IQ recordings. Here's the power spectrum at the bottom, and you can see it stopped right at 5 seconds, which is the length of time for our recording. Okay, so if you notice the frequency here is 0, GNU Radio doesn't know what frequency we used. We can tell it our center frequency is 100 megahertz, and if we play this again, it will just show that on the x-axis. But the thing is, we can tell it was 1 gigahertz. We can tell it was 2 gigahertz. It's just a software. It doesn't know. Likewise with the sampling rate. If I take this and I divide it by 2, let's say I forgot what sampling rate I made the recording at. So now, let's multiply it by 2. So now my sampling rate is 3.84, which is not correct, but it will still run. So the only thing it's going to do, it's going to go half the time. So now it stopped at 2.5 seconds. So your metadata is important. Some file types, they try to save the metadata, like here it tells you the center frequency you used. Some file types, they put metadata inside of the bytes here, and you have to know how to take it out or how to handle it, and that won't work with all software tools. Like GNU Radio, for example, it needs just the IQ data. So if we tried to use the old file before we edited it, like this one, it's gonna just crash or not work correctly. I'll show you, but in order to handle this, of what to do with our metadata, there's a third or a new IQ recording type, which is called SIGMF, and we'll save that for the next time. Okay, thanks a lot guys for tuning in, and you can see here it crashed, or yeah, it's not working correctly, but anyways, I'll save some more GNU Radio examples and introducing the SIGMF to the next video. Alright, thanks for tuning in guys.